All right, class. So we're going to talk about the brain today. We're going to do cranial nerves separately. I felt like last time was a little long. I'm going to try to keep it shorter this time and maybe do 2 or 3 videos instead of cramming it all into one long video. It's harder than I thought it would be to just talk to the camera. Okay, so we're going to talk about the brain. This is a picture, obviously, of some neurons with some of the glial cells supporting it. And so this is what a very close-up electron microscope picture of the brain would look like with some color, probably some computer-generated color. So you have to know your brain anatomy. Again, this is one of those things. There's no sense in me showing you and pointing to every word and pointing it out. You're just going to have to learn it. I'm going to point out the big things, the stuff it's important to me that you know. You need to know your ventricles. Here are your lateral ventricles. And then you need to know your major lobes. Like, you have to have these down. So when I say occipital lobe, you know what I'm talking about. So these are your occipital lobes in the back where vision takes place. Then you have your temporal lobes on the side here, and then frontal lobes there in the front. Okay, and it's the same on both sides. Your brain, at least when you look at it, is a perfect mirror image of it. When we get into function, there's some things that are different. Okay. So our major surface landmarks, just to be clear, we have, when you look at a brain like this, the little ridges, the parts that poke up are called gyri, okay? Gyrus is singular, gyri is plural. And then the little spaces in between are sulci, sulcus singular, okay, sulci plural. So you have this big part here, this is your cerebrum, and then this little kind of part that looks like a bunch of little worms together back here. This is your cerebellum, and then you have your brain stem. And we're going to go into these in detail. All right, so joining, you can see, this is a real brain, you can see in that crack there that there's something joining the 2 hemispheres together. And that big, dense, it's a bunch of white matter axons that cross there. That's called the corpus callosum. That's very important. That's how the 2 hemispheres talk to each other. Okay. In general, you have your primary cortex, and then your associated cortex, and we're going to get into detail on those. Here in the front, you see the line here. This is the central sulcus. It separates the frontal lobe from the parietal lobe, and then in the back, we still have our occipital lobe there. Your cerebrum is the seat of consciousness, perception, thought, and motor control. Sounds like a test question to me. The cerebrum is the seat of consciousness, perception, thought, and motor control. Okay, so we're going to separate out our lobes into function, and these are generalized terminology. It's not perfect. It's not like every single thing only happens there, and we found this out the hard way with people that have had brain injuries, that you can take out a part of a brain here or there, and another part of the brain will take over. Now, some parts of the brain you just can't do without. If you lose them, that function's just gone. And a famous one is Wernicke's area here. And if you lose that, you just lose your ability to understand speech. And the John Green video and that Human Anatomy and Physiology crash course that I've been recommending, his video on this is really, really good. It'll help you get this down. Okay, so frontal lobe, this is cognition and speech. And it's also your primary motor control. Like I said, motor is in front of the central sulcus, sensory is behind. So that's the somatomotor. Somato means body, motor means movement, right? Also motivation and mood is in the frontal lobe. Your parietal area, that's back here, this is somatosensory. This is where you sense things, and we're going to go into detail on that in a minute. And then, of course, occipital is vision, as we've already mentioned. Your temporal lobe, this is olfactory and auditory input. And it's also memory and learning. Very close association between smells and hearing and learning. That's why those things go together so well. Sometimes you'll smell something you haven't smelled in a long time, and it just brings you back to an ancient memory that you totally had forgotten about, but that smell brought it up again. And that's because all these things are so closely tied together in the temporal lobe. So we have our psychic cortex also, which is abstract thought and judgment. People that have damage here are not good at abstract thought. And the insula, you have to pry apart the temporal lobes. You can see in there that is the integration of taste and hearing and visceral sensation. And that's why, pressure inside your stomach is part of the enjoyment of eating. All that is closely tied together in the brain. Okay, so this is our primary somatomotor cortex. This is that gyrus right in front of the central sulci, your primary motor cortex. And this is what we call a homunculus. And this just lays out where on the brain these motor functions are. So face, lips, all your facial movements here, hand. Notice what a big chunk of brain real estate is devoted to just your hand. That's why your hand's such a powerful and why you can do so many things with your fingers, because so much of the brain is devoted. Each finger takes up as much part of your brain as, say, your arm does or your shoulder. It takes very little brain power to move your trunk. It just only does a few things. And here's feet and ankles. Now, people that are born with no arms, that spend their whole life using their toes, if you could show their homunculus, obviously, there would be more brain real estate devoted to functioning their toes, but this is in a normal person. Tongue and the vocal cords also, obviously with all the sounds we can make, and some humans can make more than others, a lot of area there. Now we're looking at your cerebral nuclei. These are nuclei that the axons from the bodies that the neuronal bodies that are up here in the cerebellum, they have axons that travel down, and that makes what we call tracks. A whole bunch of axons together become white matter tracks, so that you can communicate both ways, both sides, across and down, and there's these crossing tracks. I don't expect you to memorize all the different names of the tracks and nuclei, but you need to be familiar with the terminology. So this is planning and coordinating muscle activity. The reason we have such smooth and perfect muscle action, we learned some about muscles, but it's also the way they get the nerve signals. And we're going to look at that in more detail here. So here, the brain plans what it wants to do, but there's also information coming from the muscles that are saying, hey, this is what the muscles are doing now. And all that goes through not only those nuclei in the thalamus that we were just showing, but also in the cerebellum. The cerebellum smooths out all your muscle decisions. And so people that have cerebellar damage or cerebellar pressure from a tumor or some problem, they have what we call ataxia. Their movements are very jerky and not consistent, and that's from cerebellar damage. And so they don't, they have to think through the movements. It doesn't happen naturally. When you learn a skill, how when you learn a new skill, like say drumming, I'm trying to learn the drums right now. When you first start doing something, you just can't quite get it. And then all of a sudden something happens, and now it's happening smoothly, and you don't have to think about it. And if you wanted, you could have a conversation while still doing that movement. That's because it's become a cerebellar movement. Your cerebellum has learned it, and it no longer requires the conscious thought to make it happen. You just tell your cerebellum what you want to happen, and it happens. So I'm not there with the drums yet, not even close. So this is our primary somatosensory area. So this is behind the central sulcus. This is the primary somatosensory cortex here. And this is where we have our sensation of things. And in general, you sense the right side of your brain senses the left side of your body, and the left side of your body senses this side. Now that's not true with the face, because the face has cranial nerves that come straight there. But everything below the cranial nerves that goes through the spinal cord, there's a crossing that happens. Okay, so here we have our sensory homunculus. So you see how much of the brain space is devoted to your lips and your tongue, which is why, putting your lips up against something, whether to eat or to kiss someone or whatever, is such a pleasurable sensation. You have just lots of nerve endings and lots of parts of your brain associated with that. The hand also, again, hand's very sensitive lots of brain area devoted to sensation in the hand. And, you know, despite our society's obsession with all things sexual, there's actually very little area that's devoted to the genitals, which I've always thought was kind of comical the way our society is. Okay, so this is special senses: vision, hearing, smell and taste, and equilibrium. You know, your sensation of where things are in space. You know, you can walk even with your eyes closed because your feet feel and you know how the ground is. You have some image of what's happening there. And all that, a lot of that comes from your cerebellum being good at smoothing out those movements. So vision, your primary visual cortex is back here in the occipital area. Hearing, the primary auditory cortex is in the temporal lobe and the insula. You know, the insula is in there. If you pull the temporal lobe out the way, you can see it. And then smell is your primary olfactory cortex. And we're going to see when we get to the olfactory nerve, which is cranial nerve 1, that it's just a very, very short distance from your nose to where the brain olfactory area is. So that's one of the reasons why smells are such a powerful motivator. You can't stand to be in a room where it stinks. You really enjoy smelling something pleasurable because it just goes straight to those part of your brain that perceive these things. And then the orbital frontal cortex, this is the integration of olfaction, gustation, that's eating, tasting, and visual information. So again, there's this close association between the way food looks, the way it smells, and the way it tastes, to the point that it's hard to even separate those out. If you take somebody's smell, if they don't cover their nose and you cover their eyes and just let them taste, taste is a very limited sensation. All right. So language, we said Wernicke's area is recognition of written and spoken language. And this also formulates phrases so you can communicate back. So with damage to Wernicke's area, either from trauma or from a stroke, you have just a complete inability to read or understand what other people say. And then we have Broca's area, another place that commonly assaulted in stroke victims, is the inability to produce speech. They can understand what's being said, but when they go to say it, it just comes out gobbledygook. They just can't make the sound. So your prefrontal cortex is all the planning and mood production, and then this is your motor speech area, and then back here in the center area is the understanding of words. Okay. And then procedural memory and declarative memory are actually two different things, and they found this out. You can watch a little video about this patient. I think his name was HM. There's several good videos on YouTube about it. I usually show it in my class about this guy who was totally incapable of forming new memories. He couldn't learn anything new. He wouldn't remember. If he saw you in 10 minutes, he wouldn't remember. But if you taught him a motor skill, he could actually get better at the motor skill. So he could get better at procedural memory, even though he couldn't retain any facts about it at all. He wouldn't remember that he'd practiced it, but he'd get better at things, which is astounding. Okay, so this is your limbic system, and this is important for emotion learning, and it's also your gratification and aversion centers. Controls visceral function via the autonomic nervous system, and it's your emotion and mood. So I'm going to teach you a secret. I usually like to teach my class this in person. I hate that I can't, but if you can learn a fact and associate it with a powerful emotion, that fact is yours forever. As long as you don't have much emotional involvement in what you're learning, you'll be constantly just trying to put information there that will not stick. But if you have any emotion associated with it, then it's yours forever. That's why when you miss a question on a test, and you come back to it later, you forever remember that if you were upset about not being able to remember it, because you have that emotion of being unhappy or angry or sad associated with it. And so if you can learn things in an environment that's similar to the one that you're going to regurgitate the information in, that is helpful. And also if you can create what we call a memory tower, you know, some place that you know very well, that you have a strong emotional connection with, like the house you grew up in or the road that you travel from your house to town. And then along the way, you put the facts as you picture yourself walking through that memory tower or driving down that road. if you put the facts associated with each spot along the way, you'll remember it better. So the people that have specialized in this are the kind of people that do memory for a living. You know, there's people that like they'll hand them 12 decks of cards in a certain order and say, you have 1 hour to memorize these and you have to tell us the order. And the way they do that, they don't just memorize the cards. They make a memory tower and they put those cards along the path to wherever they're going. You know, each mile marker, each tree that you know really well has a card associated with it, and that's how you remember. So emotion is a big part of learning. This will help you all through your college and post-college career if you can find little tricks to learn things, because very few subjects are interesting enough that you just want to learn it for the sake of learning it. Although there are things like that, you know, everybody has their thing that they get excited about. Okay. So in your brain, we have our reticular formation, and this is in the cerebrum. Okay, the reticular activating system. This processes information and associated with alertness. So when you wake up in the morning from sleep, you know, you've been on alert, as unalert as you can be. And then there's that little foggy window, and then boom, you know where you are, you remember what happened yesterday, you remember what's going on today, you're back to full alertness. That's when your reticular activating system is back, ready to go. And this is necessary for consciousness, you know, what separates us from all the rest of the animals that are not conscious. Okay, we're going to talk about cerebral lateralization. We already mentioned that the right side is different from the left side. Even though it looks exactly the same, there's some differences. So in general, and these are gross generalizations, everybody's different. Let me see where we're at time-wise. Okay, in general, the left side is categorical, it's the seat of language, and it tends to be more analytical. And the right side is more artistic and imaginative, and it does spatial learning. Again, so this is generalities. And so some people are more right brain, some people more left brain is the terminology we use. And we mentioned that the motor, Broca's area, and then Wernicke's area, this is just on the left side of the brain. It's not true on both sides. Musical ability is on your right side. Artistic stuff tends to be on your right side. Now your visual fields, and this is a little confusing. It's going to take what have I done? Your visual fields, this side of your brain, the right side of your brain, okay, sees the left visual field. And the right side of your brain sees the right, okay, the left side of your brain sees the right visual field, and the right side of your brain sees the left visual field for each eye. So there's a crossing. Some of the fibers cross and some don't. So we have this optic chiasm here. When we get to the cranial nerves, we'll talk about this. But it is important to realize that if you lose like this part of your brain, you still can only see half of the world, half the visual fields, but you can see it in both eyes because of the way this works. And this is just one of those quirky little things. If you haven't studied the brain, you would never figure this out. So we talked about the tracts, association tracts and commissural tracts and projection tracts. We don't have time to get into this in this class, especially in the current situation. So just know that they have these tracts that go down. These are axons that go from the brain down. And look, notice this is important. The causation in the pyramids, this part's called the pyramids, this is where the tracks cross, and that's why the right side of your brain controls the left side of your body, and the left side of your brain controls the right side of your body. Now, this isn't the case with the cranial nerves that come straight out the brain and go to the face and the neck. Okay, this is the midbrain, what we call the diencephalon, and this term comes from the embryonic development, how the brain develops in the womb. This is your thalamus, your hypothalamus, and your epithalamus. So the thalamus has a part above it, that's the epithalamus, and the part below it, that's the hypothalamus. So here's your thalamus. It's this big almond-shaped area, but it's larger than an almond. It's not almond size. And this is the gateway to the cerebral cortex. All sensory information is relayed through the thalamus. This is That's a fact you need to know. That's a test question. It's the gateway to the cerebral cortex. Okay, the hypothalamus, this is the major, we've been talking about homeostasis all semester. This is where homeostasis happens. The hypothalamus is the major homeostatic control center for your autonomic nervous system. And also for your endocrine system, the pituitary gland here below the hypothalamus, this does almost all your major endocrine stuff. If you don't have a pituitary gland, you don't have growth hormone, you can't make your thyroid function. You just lose all that. You can't have a good adrenaline response to what happens. So this is very important. Okay, the epithalamus, this has your pineal gland. This produces melatonin and also some salts. And so your pineal gland is intricately involved in getting sleep. I've been talking all semester about how important sleep is. You need to take advantage of your natural circadian rhythm. At night, your melatonin goes up, sleep in. It's going to be very tempting for you guys right now to just stay up all night and sleep all day, because that's just what young people tend to do without a schedule. Don't let yourself do it. Your brain works way better if you stay on a good schedule. All right. This is your midbrain. You need your midbrain does all your vital functions. Your brain stem is that's where your vital nuclei are. So that keeps you breathing, gives information to your heart so your heart knows how fast to beat. Your heart will beat on its own, like we've mentioned before, even without any input, but it's very slow. It does better if it has that autonomic information coming. We just don't have as much time for all this stuff. Like, here's the medulla oblongata that we're talking about, your vital nuclei, your pyramids where the axons cross. And this is where the information goes from your cerebrum to your cerebellum and then back to help your muscles move right. Here's the cerebellum. This is gross and fine motor control. And the arbor vitae out here, this is what gives you your fine motor control. And then the vermis, the central part in the center, is gross motor control and muscle tone. It's perfectly controlled by your cerebellum. Okay, meninges, these are the layers of connective tissue that separate the brain from the skull. And you have your, going from most superficial to most deep, you have your dura mater, and then your arachnoid mater, and it's called that because it looks kind of like spider webs in between there. And then the thin layer of connective tissue that attaches straight to the brain is your pia mater. And this is the same going down your spinal cord. Okay, your spinal cord also has a dura mater, an arachnoid mater, and a pia mater. This is a good video that explains how the the meninges are tied together and how they circulate blood in the brain, how they reabsorb venous blood from the brain. Watch that video. I'm running out of time here. The ventricles, this is where cerebral spinal fluid's made. They actually, you remember we learned one of the types of glial cells was ependymal cells. Your ependymal cells in your choroid plexus make the cerebral spinal fluid, and they make about 0.4 mLs of cerebral spinal fluid per minute. And these get circulated all through your lateral ventricles and then your central ventricles down to the fourth ventricle, and then eventually get reabsorbed into the dura mater cavity that we mentioned before. This is a video about that. Watch that video. All right. So what are the purposes of cerebral spinal fluid? Well, they help for buoyancy. It lets the brain be surrounded by fluid in the center of the skull. And as you know, you can take an egg and shake it as hard as you want, and you won't break that yolk because of that fluid that's around the yolk. Well, this is a similar system, that the brain is held protected by the water. It just doesn't move very well because of the water. And also, it gives chemical stability to the brain. It helps wash away toxins that don't have any business being in there. The blood-brain barrier, we've mentioned before, it sounds made up, but it's not. This is created by astrocytes with their little perivascular feet, making coverings of all the capillaries in the brain. And then there's also a barrier between the cerebral spinal fluid and the neurons that help protect. That's also part of the blood-brain barrier. It helps protect the brain from toxins that shouldn't go there. Okay, we'll talk about the cranial nerves next time. We have a test coming up. I'm tentatively planning for April 9th. If somebody can come up with a good reason why that's a terrible day, I will consider it. But that's the plan right now. You have homework due next week on Monday. Get on it. Okay? All right, guys. Stay safe out there.